Well, this semester we are always concerned about air analysis. Some of us may be more concerned than others about air analysis. And all the air analysis that we talked about last semester with regard to measuring things such as meter sticks applies, and hopefully you know about how to estimate the error in reading a meter stick given the situation. But we have this semester we're going to be dealing with a lot of meter readings of current and voltage and resistance and things like that. So let me talk a little bit about old-fashioned analog meters. Here's an old-fashioned analog meter, and it's a multimeter, which means it can measure many things, like the meter you've used a little bit last semester. And this meter can measure resistance, ohms, in ohms, current in amperes, and voltage in volts, and other things as well. But those are the main things we're going to use it for. And it has various scales. The top scale is an ohm scale, and then the other scales are adjustable by selecting with the switch the scale you want to use. So we can use resistance in ohms times 100,000, or sorry, 10,000, 1,000, 100, or 10, or 1. So those are your decade scales. They use the same scales to read. They all read on the green scale, the upper scale. So this particular meter, if you look at the manual, you'll find that this meter is accurate to 3% when measuring resistance. So that's all you need to know, 3%. Plus the question is, how well can you read the resistance scale? That's not a very good scale, and it's not a linear scale either. So it poses some problems, but it has a minimum of 3% plus whatever accuracy you can read the scale to. So it might be 3%, 4%, 5%, and so forth. So we'll try to not use analog meters unless they come with the piece of equipment that we're using. We will sometimes replace them, analog meters, by a digital meter. So digital meters, this is the digital meter you'll be using in this lab. And it's I think the one you've already used when we did the expansion experiment to measure the resistance of the thermistor, if you may remember that. But this is, again, a multimeter, and it has decade scales. For instance, if you want to measure resistance, it has scales up to 2 million, which means you can measure anything below 2 million, anything above 2 million. You'll get a 1 on the screen which says it's too high, I can't measure it. So up to 2 million, up to 200,000, up to 20,000, up to 2,000, and up to 200. Okay. So I have in here a 470 ohm resistor. Resistors are kind of interesting. They have a color code. This resistor has 4 color bands: yellow, purple, brown, and gold. And if you look at this little sheet, which you probably have available when you need it, it will tell you that yellow is 4, purple is 7, brown is times 1, so it's 4, 7 times 10 to the first power, that's 470. So this is 470 ohm resistor. And the last band is gold, which means it's guaranteed to 5%. So 5% of 470 is 23 ohms. So it's guaranteed to be between 470 minus 23 and 470 plus 23, which is not too bad. We can do better with this meter. So if you look up in the meter manual here, when I connect this resistance, just clip on the leads to the resistor. You can't see the resistor, it's teeny tiny. That's a 1/4 watt resistor, but it's the one with the bands we just talked about. It's right there. And inside of this meter there is a battery which pushes current through the meter, and we'll be talking about Ohm's law this semester. We've already talked a little bit about it, I think, before. And it says that Ohm's law basically says that V equals IR. So we have a 1.5 volt battery inside, and actually it's a 9 volt battery. It's a 9 volt battery, and that sends current through a resistor. And of course, the product of these two numbers has to be 9, because that's what the Ohm's law says. So the point is, with more resistance, you have less current. With less resistance, you have more current. And these meters basically are current meters, galvanometers to be specific. And they really measure current. And they're translated using Ohm's law and the electronics inside into resistance. So that's how they work. They can measure current, voltage, or resistance directly, but they basically measure current because they're current meters. Okay, so this has got, I've set this on the 2 million maximum scale, and it reads 0.000, which means it's way below 2 million ohms. I'm going to click it down to the next scale. It's on the 200 kilo ohm scale maximum. It reads 0.004. Okay. And if I click it down to the next scale down to the 20 kilo ohm maximum scale, which means it reads 20 kilo ohms at the most, it reads 0.46. So 0.46 kilo ohms. 0.4 kilo ohms. Now, the point is, on this meter, you want to use the scale that gives you the most digits, the most significant numbers. And we'll talk about that in just a second, because that will give you the least error in the meter. So 0.4 kilo ohms, 0.46 kilo ohms. If you click it down to the 2 kilo ohm maximum scale, you get all three digits, which gives you 0.467 kilo ohms, which is 467 ohms. So this is 467 ohms. So the scale you want to use is a scale that gives you the most digits, fills up these three places with numbers. And we'll see why that is in a minute. Okay. So if you read the little owner's manual of this meter, and you look up the resistance scale, which is here, you will see that on all these scales, except the bottom one, which we're not on, it's 1% accurate, plus or minus 4D, whatever that means. Okay, so it says, so the meter is reading 400.467 kilo ohms, which is 467 ohms, and it's 1% plus or minus 4D. That's how accurate it is. Okay. Well, 1%, you know what that is. 1% of 467 is 4.67, or rounded off to one digit is 5. So this is accurate to plus or minus 5 ohms. So from 462 to 472. So that narrows it down much better than the panel meter, the analog meter did before. But we're not done yet. That is, these meters are easier to read. Again, you want to read the meter with the most number of digits showing, because this is the thing you have to add on to the 1%. So 1% is 4.7%, 4.7 ohms. We'll call it 5 ohms. We're talking just in ohms, 5 ohms. That's 4%, 1% of that 467 ohm. And what does this mean? 4 digit. 4D, D stands for digits. It means plus or minus 4 digits in the last significant number. So what this means is it's not going to guarantee things any better than 4 digits, 4 numbers under that, or 4 numbers above that. So 471 to 463. So that's the range that it's going to measure in. So 4 digits means 4D means 4 digits in the lowest value digit showing on the screen. That's why you want to put as many digits on the screen as you can, because this gets pretty bad. If you leave it on the other scale, which read 0.47, so you have 4 digits there. That means between 0.51 and 0.43, which is really pretty crude. So we don't want to measure it that crudely. We want to measure it as accurately as possible. And so this is what that means. So 1%, okay, plus 1%. So we have 4 digits out of 467 times 100. What percent is that? That's about 0.9%. Okay, so this means the reading you'd make with a 467 ohm resistor is 0.9% inaccurate. That's based on the electronics inside the meter, plus 1%. 1% plus whatever this comes out to be. This is always the same, 1%. This always changes depending on what that number is. The smaller the number, the bigger the percent actually. So 1.9 ohms, 1.9%, sorry. So this meter on this scale with this resistor means that we have a 467 ohms plus or minus 1.9% resistor. And 1.9, if you want to write it in terms of absolute error, that's 467 plus or minus about 8 ohms. 1.9% of that number is 8. So they're a little more complicated actually, but they're much nicer because they give you the answer. The answer is somewhat dependent upon the value you're reading on the screen, and that's what this 4D means. So the smaller that number is, if it was 2D, then it would only be 2 digits from 469 to 465. And that would be better, and that would lower this percent to maybe something like 1.5%. Okay, so that's how you use a digital meter. You use it by putting the greatest number of digits on the screen as you can, and then applying this rather strange looking 1% plus or minus 4D, whatever the number is, times D, to get the range of values. So it's 1.9% or plus or minus 8 ohms in this particular case.